So for this chapter, or for this section 10.5 from the Briggs book, or if you're working with Stewart, what we're going to do is we are going to use the comparison test and the limit comparison test. So these are two of the, I want to say almost like the coolest tests that we're going to work on. Some of the other tests are easier, but these are very conceptual. So you have to really be clear on what you're trying to tell me in your work. I will take off massive amounts of points on exams if you do not show correct inequalities, correct thinking, correct logic. There's not a lot of math in this section. This section is much more about, I guess, critical thinking and trying to understand what it means to be convergent or divergent. So what I'm going to do is, I wrote above here the comparison test. So the comparison test says is if 0 is less than or equal to a sub n is less than or equal to b sub n for all n, then if b sub n converges, so remember b sub n is the bigger sequence. So if the series of b sub n converges, then the series of a sub n must also converge, right? And if you would think of it like two functions or two graphs, you could think of it like the squeeze theorem kind of. So if we have this, let's say that this was f of x, right? Just for a second, think about it as functions. And then let's say we had this other function down here, right? And this was g of x, right? So f of x is always going to be bigger than g of x in this comparison. So if I find out that f of x is actually approaching some actual number, then I would say it's convergent to that number. In this problem, we're dealing with series, but just for a minute graphically, let's think of this. So what I'm saying is that f of x converges, meaning that it cannot approach infinity. It cannot approach, and if I was trying to find the integral, it couldn't approach an infinite sum, because I'm saying that the integral of the infinite sum is convergent, okay? And g of x is smaller than that. So what that means is that g of x is now bound from above. So g of x must also be convergent, okay? If it follows this kind of graph. So it has a feel of the squeeze theorem, okay? And it also said they're greater than 0, so they're also bound below by the x-axis as well. So that's why it kind of squeezes it in between. Now it could go the other way. It could say, let's say that we found out that g of x, the smaller one, was divergent. Well, then that would mean that f of x, which is bigger, is also divergent, because for us, when we say series, normally we say a series is divergent because its value is approaching infinity or negative infinity. So if g of x is divergent, and we know that f of x is always bigger than it in terms of the sum, if we were dealing with series, then we would say that they are also divergent because it's bigger than an infinite sum, which must be also infinite. Okay, so it has to line up in this direction. Now, what if we find out? What if we find out that f of x is a divergent? You know what? Let's kind of scrap the graph for a second. So let's just say, what if, now let's think about the series. What if I find out that the series, the bigger series, b sub n, is divergent? Oops. So if I find out that b sub n is divergent and it's the bigger series, does that tell me anything about the series a sub n, which is the smaller series? Well, as it turns out, it doesn't tell me anything, because b sub n is bigger and it approaches infinity, or is a divergent sum. So what that means is that a sub n, which is smaller, could also approach a divergent sum, or it could converge. We just don't quite know. So it has to line up for the comparison test to work. It has to line up like this, where b sub n, the bigger one, converges, then that means the smaller one must converge. Or if the smaller one diverges, then b sub n, the bigger one, will also diverge the series. So let's take a look at this problem right here. It says, does n equal 1 to infinity of 1 over 1 plus 2 to the n converge or diverge? Okay, so what we're going to do here is we're going to say, well, I'm not sure. I don't know for sure if it converges or diverges. And I can't split it like I normally would with a geometric because the denominator has the two terms instead of the numerator. And also it doesn't feel like a geometric because of the 1 plus. The 1 plus is messing everything up. The 2 to the n, if it was 1 over 2 to the n, that would be fine. But the 1 over 1 plus 2 to the n, that causes the problem. So what I'm going to do is I'm going to come up with some new series, okay? So I'm just going to think for a second. If I have 1 plus 2 to the n, and I have 2 to the n, which one is bigger? Well, obviously that one is bigger, right? The 1 plus 2 to the n is bigger. However, what if I make them fractions? If I say 1 over 1 plus 2 to the n over 1 over 2 to the n, now the bigger number in the denominator makes it actually a smaller fraction. Okay, so now we know that the left side is smaller than the right side. Okay, so what I could now do is I could now take the series of each one of them, because if one sequence is smaller than the other sequence, then the addition of those terms should also be smaller than a series or the addition of the other terms. So I have this situation now where I can say that the series on the left is smaller than the series on the right. So I have this scenario right here. I have this, okay? And it's true for all time, okay? So for n equals 1 to infinity. So what I'm going to do now is I'm going to come over here and I'm going to check this series. So we take the series n equals 1 to infinity. This is my b sub n, right? And 1 over 2 to the n is convergent by geometric. Right, now how do I know? I know because the r is equal to 1/2, which is greater than 1. I'm sorry, which is less than 1. So that means convergent, okay? So here's the thing, okay? We know that this geometric series right here is convergent because it has an r, a common ratio of 1/2, which is less than 1. So we know it's convergent. So what that tells us then is we can now say then the series n equals 1 to infinity of 1 over 1 plus 2 to the n must also converge by comparison, or by comparison theorem. It's also a theorem as well. So this is our comparison test. We basically found out that the bigger series converges, and the smaller series, you know, if you think about it as is under him or under her, the smaller series is then also forced to be convergent. Okay, so I need to see this kind of thinking. I need to see this. I need to see this on your exam. Something that shows me you have to get the inequality lined up correctly. It seems like a little thing, but if your inequality is lined up correctly and you're doing the wrong problem, then you'll get an answer that makes no sense with what the actual problem is. So it'll make you lose like at least half the points, maybe more. So here's a warning over here. Warning, you must be explicit when using the comparison theorem as to what series you are referring to, okay? Be sure to explain why the series you create converges or diverges. So I did that right here. I said it converges by the geometric because of r is equal to 1/2. Converges or diverges. You must make a concluding statement about the original series, and that's what I did right here. The original series is convergent by the comparison test with comparison to a series bigger than it. So this little part right here is extremely important, okay? Showing me that inequality is true. Now, I've seen a lot of students get the inequality wrong just because they want it to work a certain way, and sometimes it just doesn't line up. So it's very important that for the comparison test, the inequality lines up and you're sure that the left side is bigger or smaller than the right side, okay? So let's take a look at this one. So take a minute, think of what you would want to compare. Oops, why did I use K? Let me switch this real quick. So this is n cubed plus 4n. Yeah, your book sometimes switches up to K, but I mixed it. I used the N and the K. Okay, So we have this series, the cube root of n over the square root of n cubed plus 4n plus 3. Okay, so pause the video and try to come up with a good comparison. For our class, I want your comparisons in general to kind of fit a certain mold. Your book might use something different. This is what I want for our class. So take a minute to kind of pause it and see what you would come up with. Okay, so hopefully you guys came up with this comparison. You want to compare this to the cube root of n over the square root of n cubed. Okay, because we can now say that this is equal to the n to the 1/3 divided by n to the 3/2, right? So what I want you guys to do in general, especially when there's plus signs, in general with the comparison theorem, focus on the biggest powers and pretend the other stuff kind of doesn't matter. We talk about these oftentimes as dominating terms, even though in this particular one, the dominating term isn't quite as clear in the denominator. But since it's all addition, I can promise you that this and this, one of them is bigger, and we'll talk about that in a second. So this will be the series and let's see here. If we take 1/3 and we divide it by 1/2, what will we get? We'll get what? 1 over n to the 7/6. All I did was I did 1/3 minus 3/2, and that would become n to the, we'll make them meet at 6. So that would be 6 minus, so this would be 6, oops, what am I doing here? This would be 2, 6 minus 9, 6 would equal n to the 7/6 negative, which is 1 over. So that's what I did. Okay, so this is 1 over n to the 7/6. Well, this is a good series. Why is this a good series? Why do I like this series so much? I like this series so much because it's a P series. And I know P series, I can quickly decide convergence or divergence. Okay, but first we need an inequality. So we need our inequality. Okay, so which series is bigger? Well, I know for a fact that this series on the left is smaller than the series on the right because this has a bigger denominator than this. Notice this is just n, the square root of n cubed. This is the square root of n cubed plus 4n plus 3. So this denominator right here will be bigger than this denominator, and a bigger denominator means actually a smaller fraction. So then that means I can write this now. Is less than, right? And I know that this is convergent by P series test since P equals 7/6 is greater than 1, right? So anything greater than 1 is a convergent series according to the P series. Okay, so now what we can say is, oops, let me keep writing it in blue. Then the series must converge by comparison test. Okay, so let me kind of show you guys. So again, extremely important that you name why that series is convergent. Okay, so we named that is a convergent by P series. We explained why. We showed that this is in fact less than this. So everything lined up. So the bigger series converges, right? And if the bigger series converges, then the smaller series must also converge. And we showed that. Okay, so this is the kind of writing you need to show me, not really a bunch of hard math, but a bunch of logic, a bunch of following your train of thought. Okay, so now let's take a look at another one. Okay, so let's look at this one. So this says 1 over n plus 1 ln of n to the 3/2 power, n approaches, or n equals 2 to infinity. So we got a problem. I want to know if this converges or diverges, and I kind of look a little suspicious of this one. This one looks a little bit harder, or maybe it doesn't. I don't know. So what I'm going to first do is I'm going to write this series down here. And I'm going to try to find a series to compare it to. Okay, well, I know that this is very comparable to just plain old n, ln of n. Okay, I know that for a fact, right? Because if I take the plus 1 out, this is a bigger denominator than this. So then this should in fact be smaller if I write it as a series. And don't forget to keep writing it as a series. You kind of start off with a fraction, but you want to continue to bring the series back into the problem. Okay, so we have n ln of n to the 3/2 power is definitely bigger than n plus 1 ln of n to the 3/2 power. Okay, so this is a fact, this is true. So that means we need to try to determine if 1 over n ln of n is convergent or divergent. Now here's the problem. What test do I use on that? That is not a geometric, that is not a telescoping. What am I going to do? Well, hopefully you guys see that it's a u sub. So we're going to try the integral test. So we're going to say the limit as as b approaches infinity of 2 to b of 1 over x ln of x to the 3/2 power dx. So we're going to let u equal ln of x du equals 1 over x dx. So we have a perfect u sub. So this will become the limit as b approaches infinity from 2 to b of, what would that be? 1 over u to the 3/2 power du, which equals the limit as b approaches infinity of u to the, that's a negative 3/2. So this would be u to the negative 1/2 divided by negative 1/2 from 2 to b. I'm going to bring back in what I said u was. So this would be negative 2 over the square root, and I said u was the ln of x, right? From 2 to b. So this would become limit as b approaches infinity of negative 2 over the ln of b plus negative 2 over the natural log of 2, okay? Which, as we know, is, did I forget the 1/2? Oh, I think I forgot the square root. Yeah, these are square rooted. Sorry about that. So we know this one is going to become 0 because it's negative 2 divided by infinitely large. And we know this one will become negative 2 over the square root of the natural log of 2. Now the thing is, that means convergent. Okay, so this is convergent by what? What did we just use? The integral test. Now there's one thing that I forgot to do. What did I forget to do for this problem? What did I get ahead of myself? I just saw that u sub was going to work, but what I should have checked is it positive on 2 to infinity? Well, yes, right? It's always going to be positive, so check. Step 2 is it continuous on 2 to infinity? Check. Yes, it is, because 0 is not included in the integral, nor is 1. If 1 or 0 was included, it would be discontinuous, so we couldn't use the integral test. Step 3, decreasing, since the denominator is getting increasingly large. So every time you plug a new number in, the denominator is going to get bigger and bigger, so that means it's decreasing. it means it's decreasing because the denominator is actually increasing in size. So check. So the integral test applies. We found out that it's convergent. So this is convergent by integral test, right? And I need to see the answer you get. Don't just say convergent by integral test because I think it is. You got to show me that you found the actual convergent value. So then this means then that the series must also converge by comparison test. Okay. So again, I need to see this, I need to see this, and I need to see this. And then you absolutely must show me which side is bigger than which side. I'm absolutely looking for that. All this is necessary to you guys. That's just show me your work, right? So this problem actually required much more work than some of the other integral tests or some of the other comparisons that I've done so far. Okay, now let's try this one. I'd like you to pause the video and you guys try to use the comparison test on this one and see if you get it to work. Okay, so hopefully you set this up. You built another series over here, 1 over n cubed, right? Oops, n equals 1 to infinity, n equals 1 to infinity. I should have wrote that. Okay, so now, oh, you know what, let's start with 2. We can't start with 1, right? Because if we start with 1, it's it'll be 1 minus 1, which is 0 in the denominator. So we got to start with 2. So let's start with 2. So after we fix that, we have 1 over n cubed minus 1 and 1 over n cubed. All right. These are my two series. Which one is bigger? That's the problem. The one on the left is actually bigger because you are subtracting from the denominator. So that makes the denominator smaller. And when a denominator is smaller, the fraction becomes bigger. So this is actually bigger than that, right? We know that the left side now is bigger than the right. So what this leads us to is then we're going to say, oh, well, this one's easy. This is convergent by the p-test. Right? That one is convergent by the p-test for series since p equals 3 and is greater than 1. Right? So we're done. But here's the problem. The smaller one is convergent. The smaller series is convergent. We needed this to be divergent to help us. Because the smaller series is convergent, it doesn't actually tell us anything about the bigger series. The bigger series could be convergent or it could be divergent. We don't actually know. So inconclusive. So inconclusive is like the worst thing you can do because that means you just spent all this time to try to solve this problem. And now you have to just try a new test. So let's write down the limit comparison test. This is what you do when you're not quite sure which side is bigger than the other, or if the inequality, you know which side is bigger and it just doesn't line up correctly. You use the limit comparison test. Okay. Okay, so let's look at the limit comparison test. It says, suppose that the series a sub n equals 1 to infinity and the series n equals 1 to infinity of b sub n are series with positive terms. Okay, so if the limit as n approaches infinity of a sub n divided by b sub n equals c, some number, where c is a finite number and C is greater than 0, then either both series converge or both series diverge. Okay, so it's very important. The common mistake people make is they think that this is the value that it converges to. That is not what the limit comparison test says. What the limit comparison test says, and oftentimes I'll refer to this as my test series, the one I kind of build, the one I made up to divide a sub n by, that's oftentimes referred to as my test series. So you got to be really careful with the limit comparison test. What the limit comparison test says is that if this is true, where it is a number greater than 0, and in this book, they actually allow it to also be 0 and still apply. The way I was taught, it can't be 0, so it just must be a small little, a gray area at 0. In general, I don't find it happens to be 0 a lot, so don't stress about it. But in this book, I believe they say equal to 0 is also okay. So if you get greater than or equal to 0, you can say that it is the limit comparison test applies. So this step that I have here in yellow does not actually say convergent or divergent. All it says is that the limit comparison test works. You can use it now. So, and then what it means is that either both series are convergent or both series are divergent. So let's take a look at this previous problem up here, okay? So what if I did this problem now? Let's say that we now have let me do 1 over n cubed minus 1. So the series n equals 2 to infinity of 1 over n cubed minus 1. So let's say we have this, okay, and I'm going to compare it to my test series, 1 over n cubed, right? We now have the limit comparison test. And we know that this is actually bigger than this. Well, do you see anywhere in the limit comparison test right here? Does it care which series is bigger than the other one or which sequence? No. All it says is you take the two sequences that divided the series and you divide them, or that built the series and you divide them. So I'm going to take the limit as n approaches infinity of 1 over n cubed minus 1 divided by one over n cubed. And you guys should know that this equals limit as n approaches infinity of 1 over n cubed minus 1 times n cubed over 1, which we know to be 1, which we know is greater than 0. So this means check, limit comparison test applies. So what that means is we can now use this conclusion. Then either both series converge or both series diverge. Well, we don't know how to do this series. If we did, we would have done it from the first place, but we do know how to do this one. We can say since the series 1 over n cubed n equals 2 to infinity is a convergent p series, because we know that p equals 3, which is greater than 1, then by limit, I call it LCT, limit comparison test, limit comparison test, the series 1 over n cubed minus 1 n equals 2 to infinity must also converge. Okay, and that's it. That's all you got to do. Look how little math we actually did. It's all about just thinking about what series would be a good representative to talk about and compare it to 1 over n cubed minus 1. Okay, so let's look at a little bit harder one. Okay, guys, so let me grab a little bit harder one that kind of gets the message across with this. So this becomes 3n plus 1 all over the square root of 4n cubed minus n squared plus 2. And let's go from n equal 1 to infinity. Okay, so we have from 1 to infinity. So now here's the thing. We could try to set up an inequality, and remember, I kind of want you guys to focus on the biggest terms in the numerator and the biggest terms in the denominator. So I'm going to build my test series, and I'm going to just put 3n over the square root of 4n cubed, okay? Now here's the thing. When we clean this up, this is actually 3 over 2n to the 1/2, I believe. Yeah, if I do the algebra on that, 3n over 4, the square root of 4n cubed. Remember, that's really n to the 3/2 and n on top, so there'll be 1/2 left behind. So that's where I got that from. Now here's the thing. That one, we don't know if it's actually bigger or smaller than this. I don't know if it's this way, and I don't know if it's this way. I can't figure it out. So the good thing about the limit comparison test is we don't care. All we do is we take the limit as n approaches infinity of 3n plus 1 divided by the square root of 4n cubed minus n squared plus 2. By the way, you guys, one of the reasons we have a hard time determining which one is bigger is because of the minus. Minus signs with plus signs in denominators, you're not sure, exactly how it's all going to work out. So when you subtract from a denominator, maybe it will be maybe it will be bigger than the other one, or maybe it won't. It really depends. Or maybe it will be bigger at a certain point, but then you have to go and find that point. So kind of your fail-safe is say, you know what, I don't care which one's bigger, I'm going to use the limit comparison test. So the limit comparison test says now that I have to multiply or divide by my test set, my test series, but dividing by this is the same as multiplying by 2 to the n or 2n to the 1/2 over 3. I just multiplied by the reciprocal, and this would become the limit as n approaches infinity, and this would become what, 6n to the 3/2 plus 2n to the 1/2 all over the square root 3 4n cubed minus n squared plus 2. Now I'm going to basically kind of do some shadiness right here. This is something you can't actually do unless you're working with infinity. Because this limit is approaching infinity, what's the only thing that's really going to matter? Isn't it really only going to be this? This guy and this guy, I could factor out in n cubed, and they would become 0 if I factored out an n cubed. So what I'm really going to be working with, what I really need to look at is, let me see, how do I want to do this? So what I'm going to do is I'm going to divide the numerator and the denominator by the highest power in the denominator. But the highest power in the denominator is n to the 3/2. So what I'm going to do is I'm going to divide each term by n to the 3/2, n to the 3/2. Oops. How can I write this? So if I divide this by n to the 3/2, 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 and divide this by n to the 3/2, I can do some work inside that radical. So what I'm going to do is I'm going to do limit as n approaches infinity. This will become 6 plus 2n to the -1 divided by, this will become 3 Well, now here's the kind of the weird part. I hate to say this. How can I write this that it'll make it cleaner for you guys? So I already know what's going to happen, but it's kind of cheating. But I'm technically dividing that by this n cubed, right? Because they're both square roots. So this would actually become, I guess I could write it out here, the square root of 4 minus 1 over n plus 2 over n cubed, okay? So now, if I plug infinity in here, well, this is going to become 0, this is going to become 0, this is going to become 0, and I'm going to be left with 6 over 6, which is 1, right? Because the square root of 4 is 2, which is greater than 0. So this means that limit comparison test applies, right? That's all it just told me, that I can now use the limit comparison test. So now what I get to say is, what do I know about this series? Well, I know that is a divergent p-series. We can say since 3/2 n equals, is it from 1? Yeah, 1 to infinity of 1 over n to the 1/2. I just pulled the 3/2 out because it's a constant, is a divergent p-series since p equals 1/2, which is less than 1, and we know that that is what makes it a divergent p-series. Then, or since this is a divergent p-series with p to the equals 1/2 is less than 1, we can say that the original series, what was it? 3n plus 1 divided by the square root of 4n cubed minus n squared plus 2 must also diverge by LCT, limit comparison test. Did I say that on the lesson? Yeah, then by limit comparison test, yes. So this is how you can use the limit comparison test for problems that don't line up, or you don't feel like trying to figure out which side is bigger than the other because it's too hard. The limit comparison test is complicated for students in general, I think, because they do all of this work right here. So all of this work, all of this sneakiness and everything like that, all of that was just to find out that you get 1, which is greater than 0, right? All of that work was just for that, just to say that 1 was greater than 0. And that just means that the limit comparison test can now be used. And because the limit comparison test can be used, you better, so again, here's a note. The test you create to compare to should be something you know quickly. Convergence or divergence. So the thing is you want your comparison test to be something that you quickly know if it's convergent or divergent. The moment I wrote that test, I already knew that it was a divergent p-series. And then I was hoping that when I got the limit, I'd get a number greater than 0. So then I could say that the limit comparison test applies. Because the limit comparison test applies, I can say because this series is divergent, then this series must be divergent. That's what it means right here when it says in the limit comparison, then either both series converge or both series diverge. That's what it means. So if you figure out one of them's divergent, then the other one's divergent. If you figure out one of them's convergent, then the other one's convergent. So that's what the limit comparison test does for us. Okay. So I think that'll do it for this video. We'll work on, I have a few more problems we can work on in class, but I just wanted to give you a video on the comparison test and the limit comparison test. Again, the comparison test oftentimes is thought of as a stronger test than the comparison, but the comparison is a very fast, cool test. Like it just works so cleanly. The limit comparison test, you have to do a little bit of work for, but it seems very reliable. The comparison test, as long as everything lines up, you know, it feels like, almost like math magic, like it just appears that, oh, that one's bigger than this one, so this one must converge as well, or something like that. It's a really, it's a thought process you have to put yourself through for the comparison test. Limit comparison test feels more like memorize this, do this, come up with your test series. It should look similar to the other series. Notice that my test series, very similar to my original. Notice that this one, very similar to the original. Your book, some of your books just use 1 over n for like everything. Don't do that. I want you to show me that it's comparable to something similar to it, okay? But that'll do it for this video, guys. Thanks for watching. See you in the next class or the next video.